Welcome to Modeling and Simulation with InsightMaker Part 2. Thank you for, hopefully all of you were here on Tuesday because this is a continuation, of the things that I covered on Tuesday. So if you weren't here on Tuesday, it might start off a little quick. So what I want to talk about today is actual simulation models, stock and flow models, as opposed to the qualitative types of models that I talked about on Tuesday. The sequence of items available for today is about a whole day's worth of stuff. I'm going to do an overview of it, though I put all of the stuff in the outline so that you can in fact look at it at your leisure. This outline for this session you can access through the webinars page, which is where you registered for this session. It's on the discussions tab. And if viewing it in this window is too restrictive, you can click here and get a full page view of it. The outline is hot so that you can expand and contract the items as you wish. And if you double click on the link, it will open that link in a new window. All of the things that I will, almost all of the items that I will cover today, you can find in a more detailed fashion as part of the Modeling and Simulation with InsightMaker learning program, which you can access also on any page of the wiki. It's a link that's right here, which will take you to this page. But it is in fact one or two videos that talks about the creation of each of the different types of models that we figured out how to do with InsightMaker. And there's a page with notes and videos, as well as all of the individual tools within InsightMaker and videos about how to go about using them. So consider this your reference page for InsightMaker itself. It is far more detailed than the online help that's been built into InsightMaker. And as I said, this page is easy to get to from any page in Systems Wiki. The link is right here under Systemic Perspective. So I talked about on Tuesday that from my perspective, the reason that we go about creating models is given a situation that we want to address in one manner or another, and reality being as complicated as it seems to be, and everything is connected to everything else, though for a particular situation, everything that's connected isn't relevant to figuring out how to deal with that situation. So we construct models to understand how that set of interactions relate and create the situation that we're experiencing, so we can then in fact go back and figure out how to alter that set of interactions so it produces the desired state of things as opposed to the current state of things. And I talked about, we have to this point figured out how to create a lot of different kinds of models with InsightMaker. The appropriate model that you use depends upon what it is that you're attempting to understand and the level of detail that you're trying to understand that. Be aware, though, that on this particular page there are two distinct different classes of models. Most of them are what we call qualitative models. They are static views of some set of interactions or relationships, though relationships for the most part are dynamic and they unfold over time. And that unfolding, or the implications of those interactions, is something that's real difficult to intuit from a static model. So we build stock and flow simulation models to allow us to get a sense of the implications of those interactions or relationships over time. We use simulation models in situations where it's too risky or too costly to actually tinker with reality directly. We build a model and we tinker with the model to get a better understanding of how we should in fact interact with reality. Or another nice thing about simulation models is that you can use them to do time and space compression, so that the things that happen over expansive distances, over periods of time. You can get a sense of the implications of years worth of interactions in a couple of minutes, as opposed to having to wait that whole period of time to get a sense of how those relationships unfold. I said that these are a set of models that we have in fact figured out how to create to this point with InsightMaker. There are an endless array of models that are developed for different purposes. Here is a link to the model thinking program done by Scott Page at the University of Michigan. It's an online 10-week course that actually started a couple weeks ago, I think, though all of the videos, in other words, it's a 10-week course with 10 or 12 videos per week. All of those videos are accessible through this page, and I have watched most of them, and they're extremely well done. So it's the link is there, and the course is highly recommended. So in terms of a little bit additional thought about why we do simulations, this is a diagram. It's a quiz from a paper done by John Sturman, who's at MIT and teaches system dynamics. What the diagram represents is people leaving and entering a department store over a 30-minute period. And there's one diagram, graph that represents people entering, and another one that represents people leaving. And then it asks 4 questions about this diagram in terms of at which minute did the most people enter the store. Well, that one's, people usually get that one right. It's the largest point on the entering curve. During which minute did the most people leave the store? Well, they usually get that one right too, because it's the highest point on the leaving curve. Then the next 2 questions ask, during which minute were the most people in the store? Well, as it turns out, that actually tends to be is right here at minute 14, because from here to here, there were in fact more people entering than there were leaving at every minute, so that the number of people in the store was growing through that entire period, and the most people in the store is at minute 14. During which minute were the fewest people in the store? Well, that actually turns out to be minute 30, because from this time to this time, there were more people leaving every minute than there were in fact entering. So at time 30 were the fewest number of people in the store. Which all probably seems trivial now that you know all the answers. The part that you didn't know before I talked about it was the majority of people don't get all 4 answers right. And it has also been claimed that it is beyond our capacity to intuit the implications of the simultaneous interactions of 2 or more simultaneous feedback loops. And from my experience, I tend to agree with them. There's a paper that actually claims this, and it's referenced in the appropriate slide in the learning program. So what I want to do at this point is actually spend some time and create some simulations in InsightMaker to walk you through the process of actually doing it, covering some of the tools that I didn't cover on Tuesday. As I said, here are the primitives that we use to construct models and the connectors that we use to link them together, the typical action and style controls for just about every Windows program that you deal with. And today we'll get into some of the simulation tools. So let me begin with a stock. Now, a stock is something that I didn't talk about on Tuesday. Well, I don't think I talked about it on Tuesday. A stock differs from other kinds of, from a variable in terms of a stock is meant to represent a quantity of stuff that is in some kind of a reservoir or a container that changes slowly over time. Hold on, what's this? Okay. changes over time based upon an inflow or an outflow. In other words, it cannot change instantaneously. If consider it as a static kind of thing unless there's a flow into it or out of it, so that if time stopped, there'd still be a quantity of something. Think about water in the bathtub or in the tea kettle or pool in the swimming pool or the amount of water in the reservoir. It's a quantity of stuff that doesn't change instantaneously. So for the various primitives in InsightMaker, each primitive has a set of parameters that you can define, the set of properties that you can define, and they vary somewhat from primitive to primitive, and I'll talk about the relevant ones as we get to them. They all have a label, which is the name of the thing and the ability to place a note on it. For a stock, you can define whether or not it's allowed to go negative, and in this case, what I'm talking about doesn't go negative. I can assign an initial value to it, and I can also create a slider for it, which allows me to say what the initial value of it is, so that I can then use this to modify the value of that before I run the simulation. So I'm just going to say that initially this is 0. So I can move the slider, or I can type into the field to change this. Either one works. Either one's supposed to work. Come on, what's the matter? It's not working. All right, let me see what's going on. Now, as I said before, once you start a model, it's good to save it, so that, because once you save it, it will in fact then resave it every time you make a change to it. The benefit of qualitative models is you can make them say anything that you want to. You can do smoke and mirrors and hand waving, and you can explain them any way that you want. Stock and flow models, there are no smoke and mirrors. Everything is explicit. You can't get away with hiding everything. And the reason being is everything you create has a well-defined set of rules for how the connections are made and how they're interpreted and how the simulation engine interprets that set of instructions. So this, I said, the only way that you can change the stock is with a flow, either flowing in or flowing out. And just because this is in a web-based environment and the flow has to start someplace, I have to start here and draw it out, and then I have to reverse it because I actually want stuff to flow into this stuff. So I'm just going to call this inflow. And I'm going to also create a slider for it and tell it that it can change from 0 to 5. So now I've said that I have some stuff. I have a container of stuff, and I have a flow into that container. And the amount of that inflow I can set. Is this working now? But now that I've created this probably the simplest simulation possible that might actually do something, I have to tell the simulation how long to run. So I go to time settings and I tell it I want to start at 0 and I want it to run for 10 periods, and I want it to step 1 period at a time, and I'm going to tell it that it's stepping in minutes. So when I now go ahead and run this simulation, it gives me a graph that starts at 0 and goes to 10 after a period of 10 minutes, which should be sort of obvious since it runs for 10 time periods, 1 minute per time, and it adds 1 per period. Now, if I actually changed this to 2 and ran the simulation again, Now you see that it changes from 0 to 20 over the same period of time because I've doubled the inflow. So for every interaction in the model, there is in fact an explicit equation that defines how the interaction happens. Now, for this particular model, I have a stock and I have a flow. Though suppose there is in fact a maximum amount of stuff that is allowed to be in this container, whatever it happens to be. Let me go ahead and create a variable and call it max stuff, and I'll set a slider for this also, and say that the max stuff can be 20. And so now I have a slider that allows me to govern the maximum amount of stuff that I'm willing to have in this box. And let me set that at 12. Though now I need a way to control the inflow as it progresses, as stuff begins to get closer and closer to the value of max stuff. So I need to use a link to connect max stuff and stuff to inflow. Look, see, I told you there were rules. I want to connect this to the flow, but now it's laying right on top of it, so I hold the shift key and click on it, which creates a little handle so I can in fact move them around. As I said, I can't create curved lines with Insight Maker, which is good and bad. So now I can in fact define a function to say that if the value of stuff is less than max stuff, I want the flow to be max stuff minus stuff, and if it's not less than, I want the flow to be 0. So I've now explicitly defined this flow as a function of stuff and max stuff. And if I now run it again, it says, okay, it starts at time 0, and in one time period, it fills the box of stuff all the way to the maximum, which is 12. Though we think this is probably unrealistic because in most situations there's a limit on the flow itself in terms of it can only flow so fast. So let me go ahead and define another variable called max flow, and also connect that to the flow, and now change what's the matter? Oh, okay. When I initially set this up and created a flow for inflow, and because I now want it to be governed by an equation, I actually need to go back here and tell it that there isn't a slider because the slider is overriding the equation. So I have to now go back and recreate this equation again because I messed up. If stuff is less than max stuff, then what I really want it to be is the see, I want it to be the maximum of of max flow and the difference between max stuff and stuff. I think this is right. Otherwise, I want it to be 0. So what I'm saying is, if there is less than max stuff in the box, the flow that's going in can't be faster than max flow, though if there isn't enough room for max flow to flow in because it's closer than that to being full, then I have to use the difference between max stuff and stuff. A bit esoteric, probably. So if I now run this, it still goes from 0. Oh, well, the reason for that is because max, what's max flow? Max flow is currently 0. So I need to establish a slider for max flow and tell it that max flow is 5. And then set max flow equal to 2. So that the maximum that can flow at any period in time is 2. And there's no stuff when I start. So now when I run the model, it goes from 0 to 12 in one time period, which is not what I intended to do in the model, which means the equations, I put the model together wrong, or the equations are wrong someplace. So what is it that I've done wrong? If I look at this and say, if stuff, no, see, this is wrong. If stuff is, okay, if stuff is less than max stuff, I want the maximum of max flow and max stuff minus stuff. If stuff is less than max stuff, oh, it's not, all right, I've managed to confuse myself. The maximum of max flow and, oh, I hate it when I do this. The maximum of max flow. Somebody happen to know what I've done wrong? Well, let me do this first for this part. This isn't quite right, but it will it should in fact show there was an oh. All right. The equation isn't quite right, and I don't want to hold you up while I figure it out again because I've lost my train of thought. So, but what I have done is I have said that there is in fact a limit to how rapid it can in fact fill or migrate stuff into the stock. So notice that there is in fact a continual rate of filling until it gets to a certain point, and then it's full and then it stops filling. Maybe an easier way for me to do this is to change max flow and say that it varies from 0 to 1, and I can get out of this mode and say that this is then max flow times this, and this is then the same thing that was before. It's max stuff minus stuff. And this isn't max, this is now a percent flow or let's just call it a factor. So what I'm saying is that there's a limit to how rapidly that I can fill this. Oh, primitive max flow. Oh, now I changed the variable and didn't change the equation. All right. So now it says that there's a certain amount that I can flow into it based upon this factor, which was too large from what I told it to be. So if I limit it to 25%, now it should in fact do what I want it to do, which is a standard curve approaching a limit. So that I said that I want the max stuff to be 12. The stuff itself begins at 0 and fills at 25% of the difference between this and where it is each time factor. So as it gets closer and closer to the limit, it stops. And what you now have is relatively close to the situation of a person filling a bathtub with water, so that you turn the faucet all the way on, you fill the bathtub, and as it begins to get close to where you want it to be, you turn the faucet off and the flow of water into the bathtub begins to slow down until it gets to a point where it's actually full, and and when the bathtub is full, the water's turned off and there's no more water into the bathtub. So this is this is actually what's referred to as a balancing loop, which I think I talked to from a causal loop diagram perspective on Tuesday. This is one of the two basic structures that you find. As I said, balancing loops and reinforcing loops are the two basic structures that are involved in the creation of all causal loop diagrams, regardless of how complex they are. Those two causal loop diagram fundamental structures have their equivalent in stock and flow models, and so there is a balancing loop structure for stock and flow model, and there is also a reinforcing structure, and they are the two structures that are involved in building stock and flow simulation models, regardless of how complex they are. To in fact turn this into a reinforcing structure, let me go ahead and get rid of this, and I'll change the equation in here so that it's simply a factor times the amount of stuff. I'll go ahead and then set the factor to 1 and start stuff at 1. So I now have the flow governed by the amount of stuff with a factor that plays into it. And if I run this for a period of 10 times for minutes and run it, notice that it goes from 0 to 1024, which is in fact just 2 to the 10th. So that every period, however amount of stuff is in the stock, is the amount that gets added back to it. So it doubles every time period. The factor is introduced because we know that there are times when it is only a portion of the amount of stuff that's responsible for the growth, so that by introducing this factor, notice that it now becomes significantly less than it was previously. It's actually less than 10. This is if you took this factor and actually called it interest rate, what you'd end up with is the structure for a savings account, where the principal periodically interacts with the interest rate to produce interest, which is added to the principal, and it grows over a period of time, though unlikely that it's going to grow at 20% these days. So what, so in terms of doing the simulation, the result of the simulation, there is in fact a chart that's automatically produced, and you can change the values and produce additional charts so that you can compare them side by side. There is not a print capability within Insight Maker itself, but if you just use the print capability from the web browser, it usually prints. Okay, you can configure these so that you do time series, or you do scatter plots or tabular. The map is something for enhancements that are currently being done. And once you apply it, you don't have to rerun the simulation because all of the values that have been calculated are in fact stored, so that you can change the display and not have to rerun the simulation. Just change the way that you look at it, and you can also govern which things you actually want to show on the diagram simply by changing the configuration. You can add additional displays. Sometimes, I mean, if you are trying to look at two things that are extremely different in scales, there is an option to do a secondary axis, but you also might want to show one chart with two or three things and another chart, so you can add additional charts. So here's one, and here's the other chart. Okay, so far, questions? So I've showed how to create a balancing loop and mess up a formula so that I got lost in what I was doing. And a reinforcing loop, and those are the two basic structures that are in fact used to create all of the different kinds of simulation models that are possible for one to build. So at this point, I'd like to go look at a couple of examples, though to get to those examples, which hold on. There was a bug in the Insight Maker this morning, and Scott was fixing it. Should be fixed. Please clear cache and try this as possible. Okay. Oh. We'll know in a moment. Okay. This is the typical balancing loop that I showed a few moments ago, but it has a delay built into it. And let me see if it runs. Okay, it does run. This model produced an error a moment ago, so let me say. Talk about real-time demos. So what happens is, as I said before, this is the typical balancing loop where simply beginning with a desired state and a current state of 0, some amount of action is taken to move that desired state, the current state, in the direction of the desired state. And as the current state gets closer and closer to the desired state, the action in fact declines over time. Now the rate at which that happens is dependent upon this action factor that I put in there. So if I make this 0.5, you notice that it takes it longer to transition all right, then at the same time, we run into situations where the action happens, but it takes time either for the current state to actually change as a result of that action, or it takes time for the change that actually happened to be experienced or sensed by that portion of the structure that's responsible for deciding upon the next action. So that if I induce a time delay in here and run this model, it's still fine the way it is, though depending, and it has to do with how quickly the model reacts to the change. So now you'll notice that there's a slight overshoot, so that while the current state approaches the desired state, it does in fact overshoot and have to come back. And depending upon how quickly the model is reacting to the differences, the amount of that overshoot and return can be more and more drastic. And it has to do with the length of the time delay and how fast the model is interacting, so that, or responding to the difference. So now it's even more and more out of control. And if the time delay was slightly longer, notice that in this case the model is in fact completely out of control, so that the situation actually gets worse over time. So the structure of the model itself has not changed. What's been changed is the rate at which the model is reacting to the change, and the delay in terms of it sensing that change. So here is a situation where, given that the model isn't changing, the only thing that's changing is the rate of the interaction here and the amount of the delay here, and it produces substantially different behaviors with those changes. Hopefully gives you a sense of how it can be that we are simply incapable of intuiting the implications of a set of interactions, especially when there are delays in the sequence. Donald, you have your hand up. Do you have a question? If you do, you want to type it into the question box at the bottom so that I can answer it, or I'm extremely willing to answer questions if people have some. And I continue to say that it makes me a bit nervous when I do webinars and people don't have any questions. It gives me a sense that I just completely missed things on the trip. As another example, let's look at swamping insights. This is a model I developed with a person in Sydney. A situation where there are two different organizations who are offering services to families that need assistance in terms of getting off of assistance and getting employed and back into the mainstream of employment. And in this particular situation, when the model is initially put together and run, there is this portion of the model where one group of people is providing support, and that the families then move to being supported by another group of people. And running this situation, running the model itself, shows that over a period of time, the number of families on temporary assistance in this particular group Oh, good, Joseph. Glad Joseph found the comment box. The bad thing about moving from system to system, at times things appear a bit different. So because this group is responsible for providing assistance, and it appears as though they're not doing their job because more and more people need assistance as time goes on, they say, well, then for us to in fact do our job, we should go ahead and improve our capacity to help more people. So if they improve their capacity, well, let's start with 10%. and rerun the model, what happens is their capacity improves so that the number of people on assistance declines, but then it increases again. And that gives them the sense that, well, what we did was in fact the right answer, we just didn't do enough of it. So they go ahead and decide to increase their capacity to 20%, and it appears that it worked even better for a short period of time, because now the number of families needing assistance actually declined even more, though in the end it was actually worse than it was before. And if they continue on this trek, what we find out is that the more they improve their capacity, the worse things continue to get. And the reason for that is that they're not taking into account the fact that the families on assistance are in fact in a sequential process supported by different groups, and by improving their capacity to deal with families on assistance, they are overloading the next part of the process, which results in people actually not progressing to mainstream employment, but actually experiencing recidivism, so that they end up going from the second stage of the process back to the first. It's like rework. So rework in a manufacturing process, the rework creates more work for the stages that come before it, unless it's being done by completely separate groups of people, which is sometimes not. So if in this particular situation, if the second group increases its capacity to deal with those families that they are providing assistance to, and the model runs, the whole situation gets better. Even it improves the first stage and the second stage, and the overall total gets better. It's an example of, which happens extremely often, people in fact not paying attention to more than their particular aspect of a interrelated set of sequences in a process, and doing something at one stage of the process which seems to make sense, actually ending up making things worse. And it, from a qualitative perspective, looking at this particular model would be extremely difficult to sense the implications of all of those interactions. It's not until you actually develop a simulation that gives you a sense of the implications of those interactions over time. Okay? So let me also, here's another one that is something called Credit Never Happened, where beginning with a very simple balancing loop, we have a desired performance level, an actual performance level. The difference between them represents a performance gap. As a result of that gap in performance, the organization can choose to do more work or improve their capability to do work. And the model is set up so that at the initial stage, there's a balanced effort, balanced pressure to both do work and improve their capability to do work at the same time. And the situation is pretty much in a stable state, just like watching paint dry, so that the actual performance and the desired performance are the same and nothing changes. It's usually very nice to start off with a model in a balanced state, so that when you change things, you get a sense of what other things are changing. If you start off in a model, as I did in the previous one, with things actually already changing in a direction, it's more difficult to get a sense of what changes as a result of your actions. So if I now say that I want to increase, I want to add an increase of 5 units to the performance of this organization, now we notice that the desired performance actually went up. It was just a step change from 39 to 44. The actual performance increased, and there was a slight overshoot, but then it actually came back down to just where we wanted it to be. In doing that, the cost of operation increased substantially for a short period of time because the time spent working and the time spent on improvement both increased for a period of time, but then it came back in line. If we took this same model and said, okay, suppose we actually spent most of the time working harder as opposed to working smarter, in the same scenario, or for the same model, the beginning with the desired performance still makes the same step change that it did before, and the performance gap actually increases at the end, and the reason for that is that the time spent working increased significantly, and the organization began to experience burnout and actually ended up reducing their own capabilities of performing work. Whereas if the organization had spent more time, let's make it 25-75. So they spent 25% of their time working harder and 75% of their time, of the added time, working on improving their capacity to do work. You see that the cost of operation, in fact, increased as they were investing more time on working and on improving their capacity, though then the time spent on improvement declined even below what it was initially, because their performance capability actually improved, and their cost of operation ended up being significantly less than it was before. So one has to build these models for specific contexts for them to be meaningful. This was a model done for a generic set of interactions so that one can't relate it as it is to any specific context, though one can make it relative to a specific context by using all of the right values in the various places. Questions? All right, a couple other, let me see, let me go back to here. A couple other things that I should make you aware of, in that there are times when I said that everything is in fact put in with a specific formula to define the relationship between the elements, so that here there is in fact the flow is defined based on the immigration factor. There are times when the values that you need to put into a model don't fit a well-defined orderly formula. One can input using the converter primitive so that you can define during each time period what the values specifically are, so that during the time of the simulation, this defines that the output of this variable is dependent upon time, and it interpolates between these points to figure out what value to use if it needs a value. And you can define this as a continuous curve or a step function, depending upon what's appropriate to what it is that you're modeling. So here you input the values, the input value and the output value, and you specifically define what this curve is intended to be. So the immigration factor itself, as it was defined based upon the input data, and you end up with a model whereby part of the model is well-defined formulas and part of it is empirical data that has been collected. Another component that is quite helpful, get rid of this one, is there are times when you want to create connections or relations between variables, and it would be simply really difficult to connect from here all the way over to here. In this, so what you have is a function called a ghost. If I select a primitive and click ghost, it creates me a ghost, which is slightly dimmed version of that particular variable, and I can then connect that in the same way I could connect if it was the original variable itself. So using food at this point in the model doesn't quite make sense, but if I in fact wanted it up here to be able to connect to here, I could do that, and I don't end up with a link all the way around it here. The advantage is that it makes the model less convoluted. The disadvantage is that you end up with the explicit representation of loops in the model, so that here this structure right here is a reinforcing loop, this structure right here is a balancing loop, this is a balancing loop, this is a balancing loop, this, where's this go? From here to here, here, up, around this way, and back. This is another reinforcing loop. This particular one doesn't cause a problem. Well, yes, it does. There's another loop here that you don't get to see because this was turned into a ghost and put over here, so that if I connected this directly to here, there'd be another loop that you could follow. So the nice thing about ghosts is they allow you to uncomplicate the view of your model. The bad thing is that you tend to lose the explicit connections so that the loops are obvious. So it depends upon, you know, which things are more relevant for what it is you're attempting to depict and understand. The button function allows you to actually include JavaScripts in behind the scenes and perform functions. That's how I do all of the surfacing of individual components of a model piece by piece. Where was there one? There was types of models. On this particular, there's a JavaScript behind this button and behind each of these buttons, so that when I click the button, it's a JavaScript being executed to cause it to display a portion of the model. So, I mean, and there's a complete definition of the API. You can take this code and you can embed your model into a wiki page or a web page or a blog, and not only do you embed it the picture of it, you actually embed it live so that where you embed it, someone else can actually interact with the model and execute it. The equations button gives you a listing of all of the primitives that are used in the model and their values and any comments that were placed in the model. There's also, take this particular model, we run this and it shows this growth over time. If I actually take this factor and it's, well, okay, I got it on a slider at the moment. Let me turn the slider off. It has a value of 0.3. Let me go ahead and make this a random number. And tell it that it actually varies from 0.2 to 0.3. And tell it I want 50 runs of this model. Oh, I have to actually tell it I want to look at something. So it's now done a sensitivity analysis to show me the differing results where that function that's involved in the model is varying between the ranges. So it gives me a sense of how much the model results vary based upon varying the changes in the factor itself. I could have done this and actually told it to show me the how much the factor itself changes also. So now I have these are the changes in the factor between 0.2 and 0.3. The factor changed in value over time and this is the implications of the result on that factor. There's also an option to be able to, if you have functions that you want to use in the model in various places over and over again, you can in fact define macros and then use them in various places in the model. So I think that pretty much covers all of the functions that are here. It's, you know, it's a bit deceptive in terms of this is the environment. Everything is here. This is the screen on which you develop the model. All of the components that you build it with are here. And it runs, and you know, you don't have to go to a half a dozen different places to find different things, and it's extremely capable with a few pieces. So that the only thing you need to build simulation models are stocks and flows, variables and links. You can only connect, all the connections are valid except because stocks can only change based upon inflows and outflows. The only valid connection of a link to a stock is to define its initial value at the time that the simulation starts. So whereby here I created a flow that one could use to set the initial value of stuff. You could in fact create a variable and you give that a value, or actually assign a slider to it and say that it could vary from 1 to 10. And then I have to go remember to take the slider off of the stock, so that the initial value of this is now defined based upon the value of this slider, which I should then call initial stuff, just so that it makes sense in terms of how it runs. And hopefully if I make this 1, it should run in the same way. Questions? There are one other, all right. When I started building models, I used to go absolutely nuts trying to figure out where the best place to start was, because I couldn't deal with a blank sheet of paper, and I wanted to make sure that I got it right, so that I had a blank sheet of paper and couldn't get started, which meant I had a blank sheet of paper and I couldn't get started, and it was a vicious reinforcing loop that got me nowhere. Just start, just build it, play with it. The only way to get better at building models is building models, though there are in fact two different approaches that are generally taken in terms of building models. Some people like to focus on actually doing the qualitative aspect, fleshing out a description, a causal loop diagram perspective of what the problem is in the model formulation, and then they go ahead and do the dynamic aspect of it to build the simulation model. The alternative is, which I probably is my preferred approach, is everything is connected to everything else, so that I'm doing causal loop diagrams to get my head around certain thoughts, and then I'm doing simulations to find out whether or not those thoughts were correct or not. And probably the thing that I learned most painfully was build some, simulate some. The worst thing I recall is adding a half a dozen things to a half a dozen changes to a model, and then spending the next 3 hours trying to figure out where it was that I broke it. So that rather than do that, because it's completely interactive and you can do it piecemeal, add something and make sure it does what it's supposed to do before you go ahead and add some more things to it. So figure out how to do it in a piecemeal, progressive sort of way, and you never get them right the first time. After doing this for building simulation models for 20 years, I still don't get them right the first time. A lot of them end up looking like this diagram for a period of time, and you add things and you take them out and add some more things, and then realize that it really needs to be simplified. And there are times when you just say, that's it. You delete it and you start over again. Because it's a web-based environment, it's very easy to build things and share them with other people and ask for comments to give you a sense of what makes sense. How is it that I describe this situation and the interactions, so that I begin to develop a better understanding of it. So the last point that I will offer is that go back to where is it? I don't know where it is. Here it is. This link on Systems Wiki, and spend some time with a couple of these videos. And if you have specific questions about various tools, there are videos to explain each one of the functions, and build a bathtub. Okay, I mean, start simple. Don't let yourself get overwhelmed by the problem, and just do it. So, questions? Well, I hope it's been informative, even the places that I got lost. And I now have to go back and figure out how I screwed up my limits in the min-max function. Min-max always seems to drive me crazy. And if you have questions in the midst of using Insight Maker, don't hesitate to use this feedback button to go ahead and submit a question. If you find anything that's broken, let us know. Scott and I both get emails when you submit something via the feedback button, and I'm on the East Coast and he's on the West Coast, so a few hours difference, and we try to be very responsive in terms of, helping people figure out how to build models that promote understanding. So that's all I have for today. Thank you very much.